Hello, good morning to ladies and gentlemen. Are you hear me? Are you hear me? Right. All right. Thank you very much for all my students here. Right. Mohwi June. Right. Orlando. And then we have okay, Muhammad Azwan. And then we have also Muhammad Fikri, Lo, Kim, Piravan, Arun. Good evening, all of you. Okay, please join. Rifat also here. One, two. All right. So let's we continue. I hope you can hear my my lesson today. So uh, our last lesson is how to discretize the Poisson equation. Yeah, how to discretize Poisson equation. Right. So this is our last lesson. Okay, how to discretize the Poisson equation. Okay, let's we go. So now I want to explain here. Okay, how to solve the elliptic equation. Elliptic equation, for example, wave, right, which is depend on the two parameters x and y. Okay, this is the difference between the ODE and PDE, ordinary differential equation, using boundary value problem and the partial differential equation. All right. So now, okay, let's we go to the to the first part. All right. How to discretize the boundary value problem. All right. So now, I would like to share with you my chapter 9. All right. So let's we share with you like chapter 9. Go to the PDF file. Where is my PDF file? Okay. Let's I open my PDF file. Okay. Chapter 9. All right. So now this can already detected my PDF file. Okay. In chapter 9, we learn about three types of the ordinary differential equation, including elliptic equation. Right? We learn about partial differential equation. Okay, we have three types of partial differential equation: elliptic, hyperbolic, and parabolic. But today I'm going to focus on the Poisson equation, one of the type of elliptic equation where the standard of partial differential equation b squared minus 4ac is less than 0. Where is b? B is a coefficient for d squared u over dxy. So we're not going to focus on b, right? All right, because we not do the two types of derivative here, dx and dy. We are focused on dx squared or dy squared. So the condition is b squared minus 4ac, where this is considered as a Poisson equation because the fx, okay, here is not equal to 0. Is Laplace, okay, the equation here is equal to 0, right? So we also learn about wave equation considered as opposite of elliptic equation. Right? When we bring here, we can put negative. So this is a wave equation or hyperbolic equation. For parabolic equation, it depend on one first derivative and second derivative. All right. So this we call as a parabolic equation, which is depend on the two parameter u, x, and t, times and space. All right. So now we meet here today. We have a few objectives. What is our meeting today? Our meeting today is to discretize elliptic equation, right? And then how we want to fix the boundary condition, initial condition into the discretization of elliptic equation. All right. So my question is how? The answer is we use finite different method that we learn from chapter 5. All right. So now let's we go. Okay, for the uh, focus. Okay, our PDF file here. All right. So all right. So in the file here, okay, I said that okay if I go to this example, what set in your mind? The first is the boundary of x is between 0 and 2, and boundary of y is 0 and 1. And then the boundary condition when x equal to 0, okay, u is a wave equal to 0. When x equal to 2, the wave is equal to 2y exponent y. When y equal to 0 and x equal to and y equal to 1, okay, the wave will be changed to x and x exponent. All right. So the process in doing the solution of Poisson, we need to, okay, represent this boundary to this, okay, to this form, to this graph. All right. You can see here x axis and y axis. Because of delta x is 0.5 and delta y is 0.5, you can see there is a square. All right. The point that we want to investigate is a center, at the center here. All right. Because the boundary is a given in the question. For example, when x equal to 0, the wave u is equal to 0. When x equal to 2, the wave is a 2 exponent y. Okay, y is moving from 0, 1, and 2. However, when y is equal to 0, okay, the wave is equal to x, and y is equal to 1, the wave is a x exponent. So all the dot here at the boundary, there is a value. So we would just want to find u11, u21, and u31. So how to do that? All right. So to do that, we need to apply the finite difference method in the chapter 5. We discretize second order derivative to 3 points respect to x, meaning that I plus 1 and I minus 1 change. I will be changed. And then for del squared u, y squared, okay, j will be changed because the second derivative respect to y. J plus 1 and j minus 1. The rest is maintained. J is maintained to discretize respect to x, and I is maintained to discretize respect to y. All right. So as usual, like boundary value problem, we need to group the coefficient for I minus 1, I plus 1, j minus 1, j plus 1, okay, and ij. There is a 5 point involved here, all right? And then to generate the linear system, be careful the point at the corners, at the initial condition and boundary condition. Put all the real number on your right hand side. And then you know that this 5 point can be reduced to 3 point, 3 point only. You know why? Because you at the boundary, for example, u21, u22, okay, can be solved using the boundary condition and initial condition. All right. So put the real number on your right hand side. From where you get u22? From the question. Where is a u22? u22 is here. Okay, when x equal to 2 and y is equal to 1. All right, so it's here. It's a xi exponent. All right, so you are very lucky because now you can reduce the 5 point to 3 point. So that's why you can see all the answer in 3 point, 2 point. So you can create the linear system. All right. So you learn already how to solve a linear system from the chapter 2. So you have to find the wave when x equal to 0.5 and y is equal to 0.5. When x equal to 1, y equal to 0.5, and x equal to 1.5 and y equal to 0.5. So you have a 3 by 3. You can solve using Gauss-Seidel. You can also solve using Thomas algorithm. Where is Thomas algorithm? In chapter 2, page 458. Page 58. All right. If you don't want to use iterative, you can use direct method using Thomas. What you get? You get all the wave at the center point. Yeah, not at the boundary because boundary is a given in the question. Yeah, at the center here. U11, U21, U31. you can see that the graph is a curve, it's a slice. In the graph XY is a slice, okay, a slice of paper. The graph is a curve because it's increasing. All right, so now, okay, this is a process, okay. Now, I want to share with you how to discretize, all right. So, my focus here, okay, I want to share screen how we do one by one, how to discretize the elliptic equation. Don't worry, this is not a new for you. This is just extend. This is just, okay, we are focused, the extend, because before this we are using one parameter. Now we are using two parameters. All right. Before this we are using one parameter. Now we are using two parameters. All right. Depend x and y. Before this we have boundary condition in the corner left and right. But now you have a boundary left and right for x axis, up and down for y axis. Right. And then you are lucky because the boundary is not derivative. Right. Okay, now let's refocus. Okay, when we do a discretization, be careful. Okay, since I give this video to your Telegram, okay, I give already this video to your Telegram, so I just want to remind you again and again. Okay, we have a few steps to discretize the elliptic equation. Go to elliptic equation, example number 1. All right. So to discretize this, I'm using chapter 5, 5.11, the discretization second order derivative. So I derive uxx, apply, okay, derive respect to I minus 1, I and I plus 1 divided by h squared. Okay, and then this is a derivative respect to x, second order derivative. For respect to y, second order derivative, I focus on j. Uij minus 1 minus 2 uj plus uj plus 1. I focus j. And then, which is I want to maintain, I put I for the second order derivative respect to y, and I put j for the second derivative respect to x. So you can see here, it looks like I'm putting the an important derivative to the u. Okay, u is a wave which is respect to x and y, which is depend on x and y. That's we call as a ordinary partial differential equation. Okay, so now you times delta x every both part, okay, because we want to make it more simplest, okay. Sometimes you need to times delta y for every both part for hyperbolic. So, but now I want to, you focus for elliptic, you times delta x every both part. So you can get a lambda. Lambda is a delta x over delta y, all right. Since delta x and delta y is equal, so lambda is equal to 1. Kan? So now the next step is you group the coefficient. There is a parameter, there are 5 parameters, ui plus 1, ui minus 1, and then uj plus 1 and uj minus 1 and uij. So you have a 5 point here. You group the value of the plus minus, j plus 1, j minus 1, I plus 1, I minus 1, and then put the values of h, 0.5, yi, the value of y, and then you can see here, you create 5-point grid based on the I plus minus 1, j plus minus 1, and ij. All right, let's withdraw. You can see, okay, j is a time step, j is increasing, and I is a grid at the x-axis, right, at the x-axis. You can see here, this is a 5 point of the discretization Poisson equation using finite difference method or chapter 5. Okay, we are using 5.11 formula. Okay, now the question here, how to find the 3 point. Okay, U11, U22, and U33. So this is my question, right? How to do that? All right. So to do that, you need to generate one by one. All right. You need to generate one by one when I equal to 0, when I equal to 1, when I equal to 3. Same as what you done in the boundary value problem. Alright? Okay. So now let's we go to the next step, how to generate the grid for elliptic equation. Don't be confused. Don't be worried about the two parameters that we involve, xi and yj. All right. So now to discretize the grid. I already mentioned just now there are three grid. When I equal to 1, j equal to 1, I equal to 2, j equal to 1, and I equal to 3, j equal to 1. All right, because we want to find the wave when j is equal to 1. J equal to 2 and j equal to 0 is a boundary, is a given in the question. All right. So when you discretize using the star function that I discretize using finite difference just now, you have the point at the corners. For example, u10, u01, you have a point at the corners 1 and at the corners 2. All right. So at the corners 1, you use formula 1 at the boundary. All right. All right. u0j is equal to 0. uj0 also equal to 0. All right, you can see here. Okay, all right. U for j is a true exponent yj. Sorry, here u for j is a uh, true exponent yj. All right, so you have to know to find u11, you need to find 3 point at the boundary. Yeah. So you replace u12. U12 also at the boundary. Okay, U21 is not in the is in the boundary. So where is a U21? Okay, when x equal to when x equal to 1, okay, this one, okay, when x equal to 0.5 and j is equal to 1.0, so you need to use u12 is equal xi exponent, you need to press your calculator. So you can see here, u12 is a 1.359, all right? Xi exponent is 1.359. That is a boundary. So you have a real number, bring all the real number to right hand side. So you will get 2 points here. All right, you get 2 points. It's a U11 and U21. Keep inside because we want to generate another linear system when I is equal to 2, j is equal to 1. All right. So this is a point at the center. Okay, to find U21, you need a boundary condition at the above, down, left, and right. All right. So you can see here, okay, U20 at the above, below, U22 at the above, okay, up. All right. So you can use UI0 xi. Okay, xi you put I is equal to 2 is equal to 1, and then I is equal to 2, and then j is equal to 2 also. So xi exponent is a 2.718 because I equal to 2 is 1. All right. So in this case, you have 3 points. The rest 2 points at the boundary is a real number you get from the question. You bring on your right hand side. Okay, now the same formula, the same star you apply for I equal to 3 and j is equal to 1. Okay, and then what you can get, okay, you can get here, okay, you can get here is a you at the boundary, where is the boundary? On the right hand side is a boundary, u22 is a boundary, u30 is a boundary, all right, and then u21 also boundary, u41 is a boundary, all right, is a boundary. So you insert the value at the boundary and then initial condition, you put the value, the real number, and bring on to the right hand side. Okay, now you just left hand side as a u21 minus 4 u31, all right, equal to the formula on the right hand side. So what you create now, you downgrade from 3D, from 5 dimension, five grid to 3 grid, okay, to 3 matrix, 3 times 3, 5 times 5, all right. So you downgrade to 3 by 3. All right, so the rest you have no problem, because once you transform the linear system 1, 2, 3, okay, when I is equal to 1, 2, 3, you create, okay, a matrix form. Okay, 3 by 3, matrix A, the element of matrix A, the parameter is a U11, U21, U31. Then the real number is on your right hand side. Don't worry, because, all right, this is a solution similar to the chapter 2. Okay, it's using the Gauss-Seidel to solve a linear system, same as chapter 2. Okay, however, the parameter now is in 2D. X equal to 0.5, X equal to 1, X equal to 1.5. All right, and then J is equal to 0.5. You can solve this problem using Gauss-Seidel. You can solve this problem using Thomas algorithm in page 53. All right, if you want to solve in direct method. If you solve Gauss-Seidel method, all right, the iteration will stop where the value of u minus the value of u at the previous time step is less than epsilon for all the points. How many points now? 3 points. So if you have this condition or less than epsilon, stop the iteration, and then you will get the value of u. U is a wave for a specific point, all right? So what you need to set in your mind, okay, you have 5 points, downgrade to 3 points because there is a value at the corners, all right? So this is your focus, okay? Your focus is a downgrade the value. So what is the graph? So the graph is depend on the point that you generate. When x equal to 0.5, x equal to 1.0, x equal to 1.5. All right, or I put as a u11, u21, u31. The y is only at the center, is when y equal to 0.5. Y equal to 1 and y equal to 0 is a boundary. Get from the question. So what you do now is you are drawing a slice of the Poisson equation, elliptic equation. Okay, elliptic equation here, and then okay, the graph is a curve. It's a increasing. The graph is a increasing. That's I want. All right, that's I want. Okay, now my question to you all. Okay, my question to you all. Okay, how to generate the linear system of equation. So this is my question, right? My question is how to generate linear system of equation, and then how you transform the linear system of equation to the matrix form, all right? So the tips you need to remind is when you have a boundary condition and initial condition fit in the linear system. So what is the impact from the 5-point discretization of the Poisson equation? You can reduce to 3 points because there is a real number. There is a number at the corners, and bring the number to the right hand side. All right. So you will get the parameter. What you want to find is a u11, u21, u31. All right. Okay. So to solve the linear system is depend on you. Okay. How to solve? Okay. How to solve? So this is my next question. How to solve a linear system of equation? Now you come back to your chapter 2. Okay. Okay, because this one is not one line, this is a slice. For example, the graph is increasing, a slice, increasing slice. All right. It's not like a line. It's not like a line and then parabolic like this. is a slice. Okay, it's a slice. So it's depend on the two-dimensional U11, U21, U31. So it's depend. Go to page 58. You can apply the Thomas algorithm, not Thomas method. Thomas method is depend on the factorization of LU. Thomas algorithm, just fit in the formula, you will get the result for the all the parameter U11, U21, and U31. How to confirm? Press your calculator to confirm and then use equation 3. All right. Okay, now. Okay. Now, I love if I can share with you, okay, the other opposite of elliptic equation is a hyperbolic equation. All right, don't think so much. Okay, you just focus on a Poisson equation. However, if you have a hyperbolic equation, how it look like? Okay, hyperbolic equation. All right, how is look like? It's like elliptic equation, but the notation of del squared u y squared is a negative, is minus. That's all. The way you discretize similar to the Poisson equation. All right, but the change sometimes I change with the boundary condition. All right, I change with the boundary condition. All right, so now before we go to the hyperbolic equation, I love if I can go to chapter 9. All right, good. I'm stop sharing. I go to chapter 9. I want to go to the exercise of the chapter 9. I just want to recognize which is the elliptic, which is the hyperbolic. All right. So the question here, you can go to this question. All right. Exercise 9.1. I just want to let you know. Okay, let you know. I focus the question 9.1. Okay, you can see here. Okay, what I'm doing now is discretize the elliptic equation, whether it's a Poisson equal to 0 or not equal to 0. And then the boundary condition is a without derivative. Very easy. And then you have to know the size of interval is 1/3. All right. You want to solve this equation when x between 0 and 1. Okay, meaning that the grid will be moved from 0, 1/3, 2/3, and 3/3. All right. So solve this problem by discretizing, insert the boundary value problem, generate the grid. How many grid you need to generate here is a matrix 3 by 3. Okay, matrix 3 by 3. All right. Okay, because there is a point x0, x1, x1, x2, x3. Okay, 3. And then y also x0 is a given in the question. And then the last also given in the question. So maybe you need to have a few grid inside the boundary. The second question is between 0 and 1. Delta H is a 1/3. So means that you have a 3 grid here. X0, x1, x2, x3. All right. X0 is a 0. X1 is a 1/3. X2 is a 2/3. And then x3 is a 1 all right. So you discretize using Laplace. Okay, so you can see here all positive. Okay, all positive, del squared u over del y squared. All right, this one also positive, del squared u over del y squared. However, hyperbolic is different. Hyperbolic, okay, the question is a minus. Can I get the question here? Yes, 9.3. If you bring del squared u over del t squared minus del squared u over del x squared minus. Okay, this is a hyperbolic or wave equation. This one also minus. Okay, del squared u over del x squared. All right, so the difference is always minus the second term. This one also minus 1/4 del squared u over del x squared. So wave equation is depend on time. Sometimes we replace y as a t. Alright, the rest is a boundary condition. Be careful, sometimes, okay, you have a boundary condition with derivative. This one is a boundary condition with derivative. You need to use center different formula. Center different formula for first order derivative that you learn in chapter 8 boundary value theorem. Alright, so now I'm stop sharing here. Alright, I want to focus on how to discretize the elliptic equation. Alright, so I'm stop sharing. I want to go to how to discretize the hyperbolic equation. How to discretize the hyperbolic equation. Yeah. Okay, I'm sharing the way how to discretize the hyperbolic equation. Yeah. All right. So stop sharing. I go to the hyperbolic equation. Okay. I just mentioned just now. Okay. The difference between hyperbolic and elliptic. Okay. I just mentioned just now the difference between hyperbolic and elliptic. What is the difference? Okay. The difference is minus del squared u over del y squared equal to 0. Right? That's all. The way you do a finite difference is similar to the parabolic equation. Similar. Okay, you apply 5.11 chapter 5, all right, for the second order derivative respect to x and y. All right, you change u, x, y coordinate to the grid uij. So when you do the first derivative respect to x, okay, you change I, ui plus 1 and ui minus 1, they're divided by delta x squared. And then for derivative, second order derivative respect to y, you change j plus 1, j and j minus 1. All right. And then what should you do? You put, okay, which is not involve j in the first term, you put j is maintain the second order derivative too. And then the second terms too, you put I. So I is a maintain. You not do derivative respect to I, you put I. You not do derivative respect to y, you put j. Alright. So now I put my I and j in the equation. It look like complex, but actually it's not come from the complex. It's come from the derivative respect to x, I, and derivative respect to y, j. That's all. When you put I and j, it look like there is a point. Okay, two parameters involved. What we call two-dimensional involved. All right, and then you times delta y every both part. You can also times delta x every both part. There is no problem. Okay, since delta x, delta y over delta x is lambda, you put lambda. Lambda ui minus 1j plus uij plus ui plus 1j equal to uij minus 1 minus 2 uij plus uij plus 1. Alright, so since there is two terms, uij on your left, uij on your right, put in a group. Alright, group the 5 point to the simplest way. Alright, uij plus 1 is the first time step. Okay, it's the first top molecule. uij, j is a time step. We put j is a time step. And then the rest, okay, the 4 point you put on the right. Okay, so see here, to get the wave for the top point j plus 1 is depend on the j. It depend on the point at the previous time step. It's the previous j. All right. However, you still using 5-point discretization. Yeah, you still using 5-point discretization. Why? Because uij plus uij is a 1 minus lambda uij times 2. Alright? So when we draw the graph, still like elliptic. What is the difference? The difference is, okay, minus. You have a minus, okay, minus ij plus 1 here. Alright? And then you want to find the top model is a j plus 1, the top molecule, the top structure when j is equal to J plus 1, the top molecule. It depends on the 4 point at the previous J as a previous time step. Alright, so this is a structure that you are going to maintain. Alright, and then you maintain this star, we call it as a star based on the 4 point, and then you generate when where is the point? Is whether the center or at the last point. Alright, so now where is the point? The point is a 5 derivative. Alright, so how to derive? Using the 5.11. What is ij? Is a uxi, comma yj. What is a ui plus 1j? Is a ux plus h, comma y. Okay, comma y. All right. So this just I transform from the coordinate to the grid form. Why? Easy for you to write, easy for you to write and fast. Okay, fast process of the discretization. All right. So now, okay, my question here. Okay, I love if I can share you a question here. Okay, the question here. Okay, come on. I hope you can answer my question. What is my question? Okay, my question. Okay, before I give you a question, there is a question from Paravan. No, you focus, I think Poisson. You try to focus Poisson, all right? So no. So now the next question is how to solve hyperbolic equation, right? So how to solve hyperbolic equation. So this is my question here. Since you know how to discretize using 5.11 chapter 5, respect to x and respect to y, put j, okay, when you do a respect to x, and then put I when you do a respect to y. All right, so how to maintain the process of the discretization. So my question here, how to solve? Based on the Poisson equation, you solve using Gauss-Seidel or Thomas. All right. However, in hyperbolic, since this is the explicit term, we have the value at the boundary. All right. So you just insert the value at the boundary into the linear system. Let's we go how I'm doing that. All right. So let's refocus. Okay. Now, let's we go to the example. Wave equation. Okay. Go to your textbook. There is an equation. The one example here. I'm just focus that example. Go to your e-books. Okay. Solve wave equation del squared u over del x squared equal to del squared u over del y squared. It seems like parabolic, but there is a negative. If I bring y to your right hand side, is a negative. All right, the y is increasing, from 0 to 0 0.5, 1.0. X is between 0, 0 0.5, 0 0.2, 0 0.4, 0 0.6, 0 0.8, and so on. All right, so they given you a boundary condition. When x equal to 0 and when x equal to 1, the wave is equal to 0. Right? So this one is very easy. The second is the initial condition. When y is equal to 0, y is equal to 0, the equation is a wave equation equal to 1 over 8 sines pi x. Please press radian to your calculator. X is between 0 and 1. All right? The other boundary condition is a first derivative u respect to y is equal to when y is equal to 0 is equal to 0. So this one apply 5.8 first order derivative. Center different formula. All right, ui respect to y, meaning that uj plus 1 and uj minus 1 divided by 2k, right? 2k. Remember, 5.8. Alright, so now we are using 5.8 and 5.11, chapter 4, into the wave equation to discretize the problem. Alright, the boundary condition, okay, the size of interval delta y is 0.1, delta x is 0.2. Okay, come on. I already mentioned how to find the n for delta x and m for delta y is a b minus a divided by h, yeah? Alright, so, but now we are using two type of the dimension, x and y. Oh, you are lucky. They are giving you the exact solution. Alright, so meaning that you can compare the result from wave equation using finite difference method with the exact solution, and you can get the error whether, okay, the direct method or explicit method is accurate or not. Alright, okay, you can compare to find the accuracy. Okay, now I have a 3-step, the important 3-step. The first step, I need to find size of interval for x. Is a b minus a divided by h. Is a 5 grid from x0, x1, x2, x3, x4, x5. What is x5? x5 is 1. What is x0? x0 is a 0. And then to get m, okay, the size of interval for y is a b minus a divided by delta y is a 1 minus 0 divided by 0.1. So there is a 10 delta y. However, we want to focus when y equal to 0, y equal to 1 only, because we cannot go for the too much, okay, size of interval, size of grid. So I want to explain here. Since they are given you the boundary condition, how many boundary condition? 4 boundary condition. Put the boundary condition or mesh the boundary condition in the graph. Alright. The first is when x equal to 0 and when x equal to 1 at the left and right. So the wave is equal to 0. The second is when y is equal to 0, x is moving from 0 to 5. Okay, you can get the formula is 1 over 8 from sinus function. So come on, you have all the value at the corner, right? 0, 0, 0, 1, 0, 2, 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 5, 1, and 5, 2. Okay, all the point at the corners is a given. It's already have. Now your function is to get the point inside the boundary. What is that? U11, U22, okay, U21, U31, U41, U12, U21, U31, okay, U32, U42. Okay, so this is the point that you need to find. All right. So now, since the boundary condition is a derivative, you need to, like a boundary value problem before, you need to discretize respect to y, or j is moving. J plus 1, all right, and j minus 1. Okay, all right, j plus 1 and j minus 1. So you can see here, j is a I 0 minus I negative 1. Okay, I comma 0, j 0 plus 1 is I comma 1 equal to I negative 1 equal to 0. So meaning that once you meet when j is equal to negative 1, you replace to ui 1. Alright, so be careful when you meet j is equal to negative 1. Alright, so how to discretize? Many times. Apply chapter 4. Okay, chapter 5, 5.11. Second order derivative respect to x and respect to y. When you do a derivative respect to x, you change I plus 1, I minus 1. When you do a second derivative respect to y, you change j plus 1 and j minus 1. Be careful which one you want to derive. Okay, differentiate respect to x or respect to y. All right, the rest you put I for second order derivative respect to y, and you put j for second order derivative respect to x. All right. So now what should you do? Okay, times delta y every both part, because we want to focus to the point ij plus 1. Okay, ij plus 1. Y is the top point, the above point, j plus 1. All right. Okay. Come on, we change lah delta y as a k, delta x as a h. Okay, easy to solve this problem, easy to write. So you can get k squared divided by h squared. This one is you change I, and then this one is a derivative respect to j. Okay, so what you want to bring now? Bring ij plus 1 on your left, because the top point now is a j plus 1. Okay, the top time step is a j plus 1. Bring. Okay, and then also you need to combine uij. Why uij? You need to combine. There are two terms on left and right. Since you bring uij on your right, the rest you bring to the left. Okay, the rest you bring to the left. 4 point you bring to the right. Okay, because uij plus 1 you bring to the left. All right. So now, what you do? Okay, you combine all the uij, all right, and then negative uij plus minus 1, all right, plus lambda squared uij plus 1, and then lambda squared ui minus 1j. So all the derivative respect to I is a positive, respect to j is a negative. Kan? All right, so now what should you do? Okay, what should you do? Just generate the grid. Before that, let's withdraw the structure of the molecule. Like parabolic is a 5-point discretization. It's a 5-point discretization. All right. So what should you do next? Next is find the solution for the hyperbolic equation. How you do the hyperbolic solution? So in this case, be careful. Okay, be careful. Why? Because you need to involve the initial value problem and boundary value problem. All right. So I hope till now, okay, you can go to my quiz here. Let's we go to my quiz. Okay. All right. All right. Okay. All right. You go to the chat. Okay. I send to your chat. Okay. This my question is yes. The answer yes. You always consider to the decimal places. Epsilon is 0.00. 4 decimal places kan 0.005. Okay, another 0. Alright, go to the okay, I'm stop sharing. Go to the quiz. I'm stop sharing. I want you to share with my games here. Okay, quizzes. I'm using quizzes. Okay, come on. You can go here. The point is given in the question here. Okay, 81121215. Please, somebody can insert to the Telegram also. Okay, please ask your friend to join. All right, I'm waiting for you to join. All right, come on, join. All right, Piravan already. Okay, join me, Piravan. Piravan, can you go to the Telegram? Can you insert the quizzes? Join. Okay. Okay, you need to call this link. Okay, you need to call this link. All right, go to this link. All right, and then find the QR code. Okay, the QR code is 5121215. All right. Okay, Firawan, if you can go to the Telegram, put inside the Telegram, people who want to join, they can move to join. All right. So I'm waiting you at the Telegram. All right, I'm waiting you at the Telegram. Come on. Want to join the quiz, please? This considered your to come on. This is real important because this considered to classify your attendance. Okay, it's used to classify your attendance. Yeah. All right. Okay, let's risk. Okay, come on. I'm waiting. Okay, can we start? Okay, let's restart. Watch your handphone. Okay, watch your handphone. Let's restart. See you at the quizzes. Right? See you there.